d'entendre le professeur George Limbert de l'université de Southampton du Royaume-Uni. Donc, Professor Limbert is a professor of biophysical engineering at the University of Southampton and honorary professor of biomedical engineering at the University of Cape Town. He's a leading figure in constitutive modeling of soft tissues with a particular focus on skin biophysics and the mechanism and typology of biological structures. His research is supported by major organizations in consumer goods, cosmetics, pharmaceutics, and military sectors. Professor Limbert also acts as a consultant for Fortune 500, FTSE 100, and SME companies, and his constitutive models are used in industry, academia, and the US Army. He holds a PhD in computational biomechanics from the University of Southampton and is chartered engineer and fellow of the Institution of Mechanical Engineering. Professor Limbert, you are welcome at the Coutume. You have 20 minutes to present your keynote.
Thank you very much for the kind introduction. Can you hear me? Ok, bonjour, Georges Limbert. Allô, ok. Georges Limbert, Université de Southampton, donc je suis basé en Mechanical Engineering, Cape Town, département de Human Biology. Ça va être plus facile pour moi de faire en français, donc n'hésitez pas à poser des questions en français, c'est plus facile à la fin. Tout d'abord, j'aimerais remercier les organisateurs pour m'avoir invité ici. C'est un honneur d'être ici, en particulier professeur ah oui, pardon. Ah oui, pardonnez-moi, j'ai un blank. Un docteur Tésir Rezgui et aussi Makrem Arfaoui de l'école de Tam. Ok, donc le plan de la présentation, on va start. Okay, so the plan of the presentation today is to give you some idea about the motivation, what we're doing, what we do in terms of, oh, you cannot see my, yeah, okay. Very strange, yeah, all right. So, give you some idea about the skin. You know, we study skin as an engineer, but we look at that as a complex microstructure, multi-scale, multi-physics. So I will give you some ideas. So my ambition today is not to delve into technical details, but more give you an idea about the type of work we do, the possibility, the tools that we use. But of course, if you're interested in the more technical detail, we'll be happy to provide them after the talk. Okay, so does anybody have any idea about what this is? No? Okay, so I'm going to give you a clue. So this is basically a facial hair being pulled from the face. That you can see the skin around the hair. It's like a gel-like substance, so it's nothing like a real solid, nothing like a real liquid, something in between. So companies spend a lot of money and time in research to try to understand how their products interact with the skin. So let's say Razor, so I work with Procter & Gamble, who owns Brown and Gillette, and they try to understand the physics of shaving. So there are plenty of applications on skin biophysics, so cosmetics, pharmaceutics, we work in that space, we work a lot with companies involved in biomedical devices, consumer products. We try to understand the basics of mechanobiology. So why do we age? How do we age? What are the consequences on the biomechanics of skin? We do some work on bioinspiration as well. So with the US Air Force trying to replicate some ability of cephalopods to change the texture of their skin, for example. Okay, so our goal is really to understand the skin from the viewpoint of an engineer. How do we model such a structure? So our work is based on different themes, so mainly constitutive modeling, a numerical technique, we use machine learning, we use physics-based modeling to unravel some of the property of the skin. So here's an example. You have all experienced the fact that when you come out of the shower, you try to use your the biometric reader on your phone, it won't work because your skin has changed texture. Okay, so if you have the ability to understand better the mechanism of swelling of the finger, you have the ability to predict it and correct such a change. So that's the sort of work that is done at Microsoft or Apple. When you think about the physics of shaving, there are a lot of variability between people. So, for example, depending on your ethnic group, whether you're Caucasian, Caribbean, African, the cross-section of the hair is different. So that has an implication in terms of cutting forces. So all these characteristics are taken into account by companies that operate in that space. So here's an example where we are able to visualize what happened in terms of the deformation. Some of the instruments, so razors are instrumented, so we're able to measure individual drag forces on each blade. So we use physics-based modeling and this type of experimental work in combination with consumer behavior. So we try to understand the physics that is between the physical attributes of a product, let's say a razor, blade spacing, material and so on, and the consumer perception. So in terms of microstructure, skin is multi-layer structure. So the top layer, which is your outermost layer, the stratum corneum, is about 10 to 25 micrometers thick. It's made of dead cell. It's a key component in the barrier function of the skin. And all this property varies within an individual. So if you think about the skin on your eyelid or on the sole of your foot, you can appreciate it's very different. So there's variation within an individual, but a lot of variation across individual according to genetic makeup and so on. So it's a complex microstructure as it is, but it evolves with age. So here you have two slides. On the left, you have a younger female subject. On the right, a cross-section of human skin of an older subject. In this pink color, it's stained collagen. So collagen is a fibrous material that's the most abundant protein in nature, and that's what gives the skin its mechanical strength, so intention. So with age, there is a significant degradation. So when I say age, it could be just chronological aging, which is called intrinsic aging, as a result of just your genetic makeup. And then you have external factor called extrinsic aging, for example, UV radiation, pollution, temperature, contaminant like tobacco products if you smoke, and so on. So here you have a good example. Pregnancy is a good example of adaptation. If you think about this truck driver, you can see the difference on the face, which is a result of being exposed to the sun, to the wind, change in temperature, potentially tobacco product as well that start to fix in the skin because skin is a very porous structure. So what we do, we try to understand better this microstructure because there are sales implications for the macroscopic properties. So that's what we do. We use the technical serial block face scanning imaging. So we take a sample, it is stained with heavy metal. So, and you probably cannot see here, but it's about 1 millimeter cube, small cube. And it is sliced with a microtome every 15 nanometer. And then you have a transmission electron microscopy that take an image and the slice is discarded. And basically you end up with a stack of images that are used later to reconstruct the macroscopic structure. So in XY we have a 7 to 8 nanometer resolution to characterize the tissue. So of course if you look at a structure like that in terms of as a material scientist trying to understand the mechanics of such a composite, you appreciate that the geometric complexity prevents us to use finite element meshing. We cannot mesh explicitly such a complex structure. So instead what we do, we extract this information as a tensor field. So we want to capture the local orientation of each fiber at the voxel level. So we use what is called structure tensor analysis. And from that we can basically generate automatically finite element model based on the voxel. So voxel is a volumetric pixel. And from that we have various interpolation schemes, so we can assign the fiber at node integration point or just element level. and output that as an abacus file. So for those who don't know, abacus is a widely used finite element code, which is widely used in academia and industry. And we also couple that with our user material subroutine. So we program whatever conceivable we need to represent the behavior of both fiber and matrix. Okay, so here just a structure tensor analysis. So basically you take the gradient of an image and then you form the structure tensor, which is simply the dyadic product of the gradient of the image. And from that you do an eigenvalue analysis where you can extract the lowest eigenvalue, which is associated with the direction of the fiber. Okay? And from then you can assign fiber at element level. So we did a lot of tests for different type of very controlled geometry. So we generate a network of fiber and then we extract to verify that the algorithm works as it should. And then in terms of constitutive modeling, we use environment-based continuum fiber reinforced composites. So we don't model explicitly the fibers, but we model their local orientation. So with each of these fibers, we associate strain energy density, and we have an energy density for the matrix, which in that case is a simple neo-Hookean material. Okay, and from that we can derive the equation we need, the tangent stiffness, and we implement that into the finite element code. Okay, and from that, then we can start to study. So I'm going to skip that, it's not too important here, but traditionally what people do when they model biological tissue as an isotopic structure, they assume that they have one or two family of fibers, okay? But this distribution of fibers is typically assumed to be uniform within the whole geometry, which we know is not the case. So there was a bit of update on that type of model in 2006 with the Gasser, Ogden, and Zaffer model, where instead of assuming perfect alignment of fiber, they assume that there's some dispersion around the mean fiber. So that's better, but what we wanted to do is to capture locally fiber orientation. So that's what we do. I wanted to compare the response. So what we do, we have a representative volume element in which we have extracted fiber orientation. And then we consider, so that one is fiber assigned as each voxel of fiber assigned uniformly, and we can see the response is very different. Of course, it's very dependent on the sample we have been using. But we calculate basically an equivalent stress-strain curve. So that can be used for then subsequent model where we can consider that we have homogenized the tissue using numerical homogenization in that case. Okay, and then we can look at distribution because typically in nature, I think everything is smooth. The only time where we don't have smooth and discontinuities when we talk about fracture, but in general, nature favor gradual transition. So I think it's important to look at this kind of behavior in nature on real tissue, because I don't believe that you have strong stress concentration or very localized type of strain in tissue. Everything is typically spread. So we can see here we have such a behavior. It doesn't mean our model is good, but at least it's a good first step in the right direction. Okay, so this technique, of course, is not just applicable to biological tissue. It could be used for any type of fibrous composite. Okay, skin friction, the other aspect, so it's very important. You're familiar with friction blister. But for many years, there have been a lot of people burnt by the deployment of airbag because of the friction burns due to the fabrics against the skin. So there's a lot of interest to understand better friction. Okay, so that's for this type of automotive application, but if you think about Apple and Samsung or any type of tactile surfaces, consumer electronics, they want to understand better how to interact with such a structure. So anything to do with friction is relevant. And here again is a simple schema we use for computational homogenization, where we show that the microstructure in combination, so the geometry of the microstructure in combination with the material property can really modulate friction. Okay, so even if you assume that zero friction at small scale, you can still generate friction at the macroscopic scale only due to the geometrical effect, and we were quantifying that. Of course, this is a very simplified model, but at least we've got a bit more control what we put in our model and the output, so to understand the effect of these parameters. Now, skin aging, so it's very important, of course, because aging of population, but there are several aspects. So people need more medical treatment longer, but people want to remain active longer. So a lot of people in their 70s, even 80s do gym, do sport, but their skin has become much more fragile, which means that they're more likely to injure their skin in that case. So companies try to understand the effects of aging on developing better material, for example, for their products, because they don't want to their product to create injury to people. So, for example, they would use softer material. And what is aging? Okay, so there's this comment. Seems to be stuck. Okay. So what is aging? Basically, aging is a slowdown of cell activity, tissue biochemistry. So that has an effect on how cells work. So they tend to produce less quality material to renew the skin. So, for example, collagen is one of those materials. Elastin. So you have a sort of interplay of the chemical property of the tissue that has an effect on the microstructure, and of course the microstructure has an effect on the mechanics. So it's a complex interplay, and that has consequences. So for example, with age, the interface between the epidermis and the dermis tends to flatten out. So as an engineer, it's pretty obvious and intuitive that if you have corrugated surface interlocking, they're going to resist shear much better. Okay, and what we observe in elderly people is that they're more likely to have injury due to shear, okay, because they are flattening of the structure. So again, these are very simplistic model, mechanistic, but we try to explain step by step simple mechanism, or at least to test some hypothesis. And then the next stage is to couple mechanics with biochemistry. So for example, when you get UV radiation through the skin, you have photochemical reaction that trigger the production of enzymes. These enzymes, in turn, they affect production or degradation of collagen and affect elastin as well. And so that's an interplay that results in change in the microstructure. So for example, tissue tends to be stiffer, tends to be more anisotropic as a result of UV exposure. Skin wrinkle, another interesting subject. Of course, it can be viewed as a purely trivial thing related to beauty and as it is the hallmark of aging. But again, that has an implication in terms of how we interact, because a wrinkled skin interact differently with fabrics. So just a quick detour to explain the physics of wrinkles. So it's everywhere in nature. If you think about mountains, there are the wrinkles or the earth crust, so they have compressive force that basically generates wrinkle. The skin of a fruit when it dries, exactly the same principle. And the typical ingredients that you have two layers. One is much thinner and much stiffer, lying on the top of a much thicker and much softer layer. So as a result of the competition between the bending energy of the two layers, you have production of wrinkle to minimize the energy of the system. And what is important in skin is that the top layer, I was mentioning, the stratum corneum, have this material property changing in a matter of hours as a result of dehydration and changing relative humidity. So it can go from 0.5 megapascal to over 600 megapascal, just as a result of drying. So that will happen if you take a long haul flight, or if you're exposed to a radiator in winter, or maybe not here. Your skin will dry. As a result, the stiffness is going to increase. So we wanted to test the effect of the ratio of stiffness, because that's often what controls the characteristic of wrinkle. So we use laser profilometry to take a real topography of human skin. And we did a parametric study where we vary the ratio of stiffness. So we show that at the beginning, for moderate ratio of stiffness, what matters is the original texture of the skin, the topography that matters the most to trigger, to control the wrinkle. After a certain ratio, what matters the most is the ratio of material properties. So this is a problem that has been studied in the physics community, but he wanted to quantify that for skin. And again, depending on the stiffness, of course, you have more of a folding structural mechanism when you get micro wrinkle. And then there are some interesting sideline of that, is that it's been observed that often cancerous cells are found in the valley below the wrinkle. Okay, so maybe there's a reason. Maybe it's related to cell activity that don't like that prefers that type of mechanical environments. But again, with simple model, we start to get some additional insight into such a system. So here you have an example of that. So it's not CGI, it's finite element simulation, so it's physics-based, and you can see the characteristic of wrinkle, the compression wrinkle in that case. So the one you will have when you smile, for example. Okay, so a quick detour to sort of main theme in our research, that we're trying to develop a statistically significant model, because we're all different, and in the future you will see products that target specific age group or specific ethnic groups. Okay, so that will be the kind of unique selling points of a lot of products. So to that end, companies want to understand better how we can model variability. So the idea is to have a model of skin which would be parameterized by age, sex, ancestry group, and so on. And here's an example of skin elasticity. So it's the difference between Afro-Caribbean, North European, Caucasian. The elasticity is very different. So these are consistent results, just to give you an example. Okay, and what we do as well is to try to understand sensitivity. So for example, a question, a company that develops a razor could be, what happens if I change the blade spacing? How is the consumer going to perceive the difference? So, because, for example, pressure on the skin is a surrogate measure of comfort or discomfort or even worse, pain. So by understanding that better, they make decisions about certain design aspects. And what we do direct sensitivity analysis, so we can do sensitivity with respect to the parameter of the material, but we can do that with respect to boundary loading condition and even the geometry. And then we can map that. So that's very important, because let's say you apply a razor head, you want to know how much pressure you might get somewhere else in the model. And that's how I think sensitivity analysis is a really useful tool. Stochastic formulation is something we've been going into more recently. Is trying to model spatial variation in properties. So basically, a stochastic field. And the idea is to use sensitivity-based propagation of uncertainties. So we use Carrier-Love expansion to basically represent the stochastic field. And then we couple that with the finite element analysis. So I'm going to skip most of the slide here. But what is important that at the end, you can basically see the effect of perturbation in your parameter. And instead of running, let's say, 10,000 Monte Carlo simulation, all you have to do is basically 2 finite element analysis. One first to capture the stochastic field. The second, which is the main analysis, and then finally you can do a simple calculation of the sensitivity using Mathematica, so it takes less than a second, based on the analytical formula. So here you have a simple Neoken bilayer structure. So here you have the deflection, the vertical deflection. You have the sensitivity of the vertical deflection, the Young's modulus. And then symbol the sensitivity, and based on that you can calculate the response, the perturbed response. Okay? So for example, if you look at that, you can estimate what would be the response if you perturb your Young's modulus, for example. Okay? In that case, now we model this as a random field, so we assume that the properties are going to vary everywhere, especially in your model. So we calculate the decomposition of the stochastic field, so you can decide which order you want to do it. And after that, you can calculate basically the response. Okay, so instead of running 5,000 Monte Carlo simulation, you get basically, as I said, 2 main phantom analysis plus a quick response of that sensitivity response. Okay, so based on a probability distribution. And here's an example. If you vary stochastically just the top layer, you can see that you have drastic differences in the response because obviously buckling, wrinkling is very sensitive to geometry. So current future work is to try to capture this stochastic field. What we do as well is try to understand the physics of aging. So by using a wide set of modalities, so with a micromechanical test, transcriptomics, basically analyzing the protein in front of the surface characterization, and then use that to learn something about the different age groups, different ethnic groups. So that's more recent work. And then work as well on digital twins, trying to replicate basically first a surrogate of skin because we want to control every single parameter. And here's a final example of the work we do for insulin delivery and glucose monitoring systems. So we do experimental tests, simulation of that. And more recently work on non-local mechanics. So trying to understand how we can model anisotropic tissue because there's evidence that tissue are non-local. So continuum mechanics assume that every material particle interact only with their neighbor, but not with their neighbor within a finite horizon. And that's where perodynamics is very, very interesting. If you're interested in more things about modeling of skin, contact me, I can give you some detail. As well, if there are any students here, we recruit. And the good thing about Tunisian students is that they pay the same fee as British students, which means that for us, it will be the same in terms of finding the funding, so it's much more easier. Finally, I'd like to invite you to the next African Conference on Computational Mechanics in Cape Town will be next year. And last slide, thank you very much for your attention. So I'd like to thank all my collaborators because of course all the work I presented is a result of many years in interaction and my sponsor as well. So thank you very much for your time.
Thank you, Professor Limbert. We have time to pick up 3 questions at most. We have to go forward and so if any question, suggestion. Yes. Please come.
First of all, thank you for the quality of the presentation, and I learned a lot about the skins and the behavior of the hair on the skin. In the future works, if the development models can predict some or predict aging, or for example, some disease can be predicted after they.
Sorry, I could not understand what you said.
Yes, we can detect diseases on the skin based on these models.
Yeah.
Before, yeah.
Is that a question? Or?
Yeah, this is a question.
Okay.
Thank you.
So if it's a question, yes. I mean that's why we work on the digital twin. Because the idea is to say if we take non-invasive measurements of the skin, so that's another good thing about skin is that it's accessible externally. So if we take measurement externally, we want to, for example, detect any perturbation in the mechanical field that could indicate that, for example, there might be cancerous cells at a specific location. So that's a sort of application where you will want to predict. But you can do image analysis as well to detect inflammation, irritation. So there are. Yeah.
In that case, we need a big database in hospitals.
I'm sorry, I cannot hear you. I'm having hearing problems. So.
In that case, you need a big database surgery, for example, and you have to develop some in situ tests before surgery, after surgery, and we have to have a big database in order to calculate it or use the database in predicting.
Yeah, so that's why we do a digital twin of a skin replicate and of the skin. Because skin replicate will be able to know exactly the geometrical property, exactly the material property. So that's the first phase. Because if we do do such an approach with skin, we don't know anything about the geometry, we don't know anything about material property, even if we can do inverse analysis. There are too many variables to, I think, to use machine learning to that properly. But the next step will be that, yeah. Thank you.
Professor Limbert, please, can you close your microphone? Okay, just close it.
Thank you, Professor, for the presentation. My question, all this work was in collaboration with well-known companies such as L'Oreal, and in the beginning of the presentation, you treated the issue of losing collagen from the skin with age. So I have two questions. The first question, since we are dealing with an issue, certainly there were solutions proposed to either to prevent this issue of losing collagen, the problem of losing collagen from skin. You're dealing with L'Oreal or other companies.
I cannot say which work I done with which company.
Whatever, yes. But you're dealing with companies who are concerned with avoiding this problem. So we're trying to find solutions, right? Exactly. So the first question, were there any solutions to prevent this problem of losing collagen, considering this study? Losing the collagen from our skin. Either before, in the age of 20, 18, I don't know, or once this problem occurs, is there any solutions after?
Est-ce qu'il y a... Vous avez compris, ok.
Merci. Oui, donc en fait, on peut faire des choses, c'est pour ça qu'il y a une industrie cosmétique. J'ai pas montré, mais on fait des études aussi sur photorejuvenation, quand on utilise des lasers. Donc en fait, on crée un plasma dans la peau, et ça brûle, ça vaporise, et les cellules se régénèrent. Donc ça, c'est un moyen. Il y a des méthodes chimiques aussi, chemical pills. Donc c'est très long, ça dure un mois, il ne faut pas avoir s'exposer au soleil, mais ça marche très bien. Donc il y a ça, hydrater sa peau, ou Photoshop aussi, ça enlève les rides.